a common interview question is, what are the differences between threads and processes? Even I ask this question sometimes. Now I'm not looking for whether you tick all the boxes, you have all the list in your head, but I find this a very good conversation starter, and then you can branch off for various system programming topics. Now, what is the canonical answer? Is that threads share memory, processes don't. Processes get a copy of their parent's memory. Now this answer is, I think it's a very good mental model. Because it catches the main feature of threads versus processes, but in detail this is actually not correct. So let's just think about, okay, they share memory. So two threads share memory. What does that mean? So that means they share the data segment, BSS segment, heap, stack, and other stuff in the memory. But wait a moment, that can be true. They can't share the stack because they run different parts of the code. So now it immediately we see that this simple mental model breaks down a bit. And there are other things in memory, like memory mapped files, and the other properties that a process can have, and process and threads can have. One of them, some of them was like file descriptors, file descriptor table. What to do with those? What to do with file locks or signal dispositions or shared memory? And there are at least 20 different things we could list here. Now, if I would give you a list like this and ask you to fill out what is the reasonable thing to do when you are forking, so you make you create a new process, or you create a new thread, and I think you will get like at least 50% of those right, because some of those are quite obvious what can be the good solution. Some of those are not so clear. Even that different Unix versions implemented them differently, or even different Linux versions implemented them differently over the time. Just to mention one example is that when you make a fork, then it's a system call fork, and it returns both in the child and in the parent. And based on the return value, you can branch off to different parts of the code. So that's how you know whether you are in the child or in the parent. So the question is that which process would, after fork, which process would run first? Now this seems like a silly question, because why would you care? I mean, it feels like that if you care about this in your code, then you are doing something wrong, right? But if you think about it from the kernel's perspective, how you would implement a fork, then probably it would be deterministic. And if something is deterministic, then client code will start relying on that eventually. And so then the question starts to make sense. What makes sense? Should the parent start first, or should the child start first? And different Linux versions implemented it differently. So another way would be that you throw a dice and make it randomized. But that's an extra work. Why would you do that? Okay, let's stop here. I will get back to the system calls a bit later. Oh, I just want to mention that forks, so processes, are implemented by the fork system call, and the threads are implemented by the clone system calls. There are multiple clone 1, 2, 3 system calls. I have created around a dozen different programs in different languages. They all do something simple, and I want to go over them and record how many threads they are using, how many system calls they make to the clone. This way we can look inside the various implementations of how like the Java runtime works, what Rust are doing, what Go is doing. I will not go very, very deep. Just the main thing I want to take away is how many threads are they using to implement a solution. So there are usually three types. Let me show it on the, for example, on the Python code. So there is usually a hello world, just prints out hello. Oh, yeah, it prints out hello. Then the second versions are usually some blocking calls where I am making a HTTP GET call to various domains and just prints out the statuses. This is what I implemented in the other languages as well. And then there is a third version where if the language supports some kind of async, green thread, coroutine kind of way to do the same task, so make a HTTP GET call to 3 domains and just get back the status and print it out, then I will compare how many threads they are using against the blocking calls, which was the previous one. Okay, so I have a very simple make file here. It basically supports single files, so it creates programs from single files and it doesn't support multi-files. So let's just build everything now by calling make. The Python one, of course, I need to do something different. So let's jump into a virtual env. Okay, let's evaluate what Python does. Let's just first run the hello world. It prints out hello, perfect, and we will use strace extensively to look inside what kind of system calls they are making. And I'm looking. Okay, if we just do this, let me show you, just as a warm up. We will see various things that all the system calls it made, and we also should see printing out hello somewhere. Yes, actually this is the standard out, and the rest was the system call. So it is intermingled. So these characters actually went to the standard error, and this one went to the standard out. Never mind, we will not take another look at this. We could, of course, we could send these to a files and then it would be much clearer, but I care only about one thing today. Is about so I send the standard error to the standard out, and I will just grep for clone system calls. This is the way how I can see that whether they use any kernel any threads, and the hello world doesn't use any threads. No surprise there, I think. Okay, I will immediately jump to the other code, which we saw earlier. It also doesn't use any threads. Let's take a look again inside what this code actually did. So here are the 3 URLs, and it uses the requests library and just call a HTTP GET on that URL, and we print out the status of it. This doesn't use any threads. It's a blocking call. Let's take a look now an async version of it. So it uses async IO, AIO HTTP. It looks very, very different, but it does the same things. So it will call fetch status. Fetch status uses session get URLs response and returns just the status of it. And it uses async IO as a runtime. Okay. So let's strace this one now. Now we can see that it actually created a bunch of threads for us. So at least one. Sometimes these are broken out to multiple lines. That's why I'm not that fast to calculate how many. 1, 2, 3, 4. But here everything is on one line. So it actually created 4 threads. Now that's a bit surprising, but okay, let's not take any let's not say anything at this moment. Now I want to point out these various flags to the clone system call: clone VM, clone fs, clone files, clone sighand, clone thread, whatever. As we will see, just keep them in mind. So what I wanted to say that as we will see that these flags will be the same for every other programming language, and this is not a surprise. As we will see in the I hope I will show it when we look at the system call itself, that many of these flags actually must be turned on if you want to claim that you are using POSIX threads. So clone VM is about cloning the memory. Clone FS is the this is not the file descriptors. It's file system data, like where your file system, where the root is, or your current directory. I think things like that. Clone files are the file descriptors, signal handlers, and various other things. Okay, let's move on. So that was Python. The only surprising things was that these async version actually created at least 4 threads. Okay, so we can exit the virtual env. What next? I think let's take a look at Go. So we created three programs for Go as well. Let's take a look at the Go hello code. It just prints out hello world. Does it work? Yes, it works. So let's do again an S-trace. Now, first surprise. So we are just using a hello world, and even that one creates a bunch of threads for us. So here is one, another one. This is the same line. This is what I meant, that it's not that simple to calculate them, but we can see the thread IDs here, and they are in order, so we can check the last one and the first one. That's another way. So I see at least 6 threads. It's a bit surprising, but Go has a runtime, so it has a garbage collector and it can do other things. But still, it's a bit of a surprise for me. Okay, not directly that. So let's take a look at the blocking implementation in Go. So again, 3 domains. It uses the net HTTP library and makes an HTTP GET requests and gets their statuses, the status code, and then later it prints it out. So the same code, I try to make the same code in all languages. Go domains. Let's see how many threads it creates. Well, a bit more than the hello world, as we see. 1, 2, 3. Okay, let's 67. I calculate 8 threads. Okay, let's take a look at the Go domains, an async version of it. Now I'm using Go routines. These are built-ins in Go as the coroutine version, and they are using HTTP GET inside them. So it's nearly the same. We sync on them to wait for all of them to finish, and here we kick it out, kickstart them, and then print it out. Okay, let's check how many threads they are using. 88. Well, I calculate around 9 new threads from this number and this number. Yeah, it looks like it created 9 threads. Okay, let's let's not say anything else at the moment about that number of threads. But I want to say what are these coroutine things, because I talked about processes and threads before, but let's talk a bit about what are these other things. So I would put under the same umbrella the coroutines, the async functions, and green threads. There are other names for these. These can mean many different things, but there is one common thing about them, and I would say that these are thread-like objects, thread-like entities in a language that are not scheduled by the kernel. I think that's the main differentiator. So if they are not scheduled, these thread-like entities are not scheduled by the kernel, how can you schedule them? How can you make this cooperative inside the same thread? Well, there are many ways to do that. One of them is like using signals. So a signal is the one that interrupts things, and that's when you can have some kind of thread controller inside that thread, and that catches the signal and makes sure that everyone plays nicely. Now this could get interesting in detail, so I just said in the high level. But as far as I know, that in a previous threading implementation in Linux actually used this version. It was called Linux threads. Now what else? Sometimes, so this is always paired with the syntactic sugar in a language. These kind of coroutines, and depending on how deep the syntactic sugar goes, it can hide things from you, or it can expose the things to you. So if you are getting exposed to it, then the language does not protect you from making a blocking call. So what could go wrong when this doesn't work is when you make a blocking call, then you are actually blocking the whole thread. Blocking call are system calls to the kernel when you take away when the kernel takes away control, because you asked it to make a blocking call. So what can happen? Okay, let's move back to the general tools for coroutines first, and I will get back to the blocking calls later. So another implementation when you get exposed to it, when you expose to the whole runtime, is when you explicitly have to yield back control, maybe with the keyword yield. You have to yield back control to the in your coroutine, so you give a chance to the others to run. Some coroutines are implemented with stacks, so every coroutine has their own stack, so they behave more like threads. Some are implemented stackless, so they run, and then if there is any kind of information they should store, that is stored in somewhere in a table. What else are in the toolbox? Okay, another way to make the syntactic sugar work better is that every function call that can block, you can call it only through the language's standard library. And those standard library functions are aware of coroutines. If that happens, then they can decide there. You make a blocking call in syntax, but that actually turns out to be a non-blocking call. How can they do this? One way is that the system calls has non-blocking versions. For example, a read function, you can read from a socket in a non-blocking way as well. So that's one, but that does not alone that does not solve everything. But if you use also things like epoll, which gathers these kind of blocking requests that you want to make. So for example, you want to read from a socket, and instead of calling a read from a socket blocking or non-blocking way, you actually just register in the epoll context this request that you want to read from this process, and then you yield back to the coroutine controller in your language the control. You give back the control, and of course it is marked where you are in your function. Then if all the functions, all the other coroutines are sitting inside an epoll waiting, then they actually the coroutine controller calls an epoll wait, and then whatever can run after that next, those coroutines are handed back the control. So your seemingly blocking call gets returned, and that's where the coroutine will continue talking. I showed epoll in a previous video in detail in the Unix video. I will give it a link. I will not want to talk more about that. But so basically these are the toolboxes, and whether how much syntactic sugar you want to add to it, it depends on the language. So the main takeaway is these kind of green threads, coroutines, async things are not scheduled by the kernel. That's the main differentiator. Okay, let's go back to the languages. Maybe let's take a look at Java now. So I have actually just two versions of Java here. I have a hello world. It just prints out hello. By the way, my Java is OpenJDK 17. So there are multiple Java runtimes, Java VMs. Okay, let's run now Java. How to run Java? Hello. And now we, as before, we are just looking for how many threads it creates during a runtime. Oh my God, that's a lot of threads, right? 8821, 8838. That's a lot of threads. So okay. Now let's. I'm curious. So the first time I saw this, I basically I was laughing and fell off my chair because this seems ridiculous on the first when you first saw it, and it still is a bit. So let's take a look at exactly what they are doing. So one way is to so why do we have so many threads? We can take a look at strace output, but oh boy, this would be a long one. Another way is that to run it and stop it. I can't be fast enough. Okay, I will do this with another Java version. Or we can actually implement. We could add a sleep into it, and then I can stop the process. Okay, let's move on quickly to the other one, and then we will stop that one, and then I will continue this conversation. So the other one was called Java domains, but first let's take a look at its source code. Domains.java. So it uses the built-in HTTP URL connection. We have these three domain names, and request method get and gets the status code and just prints it out. Same code as before, just in the Java world. Okay, buckle up, people, because this will be long. It even ran a bit longer than anything else so far. So 1847. Oh my God. So it has around 30 threads in total. That's how much it created. Did I calculate it well? Yes. It's okay. We don't see all of them. 82. Yes, around 30 threads. Now we can do what I wanted before, is to actually stop it while it is running. Okay, I pressed Ctrl Z to stop it. And now we can take a look at the different threads. And for that we will use the PS command. This is the PS command that that will print out the parent ID, the thread ID, the command line, how the main program started, and potentially the thread names. That's what we are looking for. Not every language names their threads, but Java does. Okay, we don't see all the threads because I stopped it somewhere, and maybe some threads were created and stopped since then, but we see enough to understand how many things are going on. So the garbage collector has at least 5 threads, and they are all named. So we can actually look these up probably in documentation. There is a VM thread. I don't understand everything. The finalizer there is a reference handler, a signal dispatcher, service thread, various compilers, sweeper, notification. I don't understand. Now this is big. I can't really recommend Java to anyone. Oh my god. Yeah. Okay, I gave it a silent 1 second, and let's move on. So that was Java. Now, you would hope that Rust will do a lot better, right? So I have a Rust Hello World and two other ones here. Because this was the easiest way, so I depend on a few other libraries, but in the Hello World I don't depend on anything. So I was able to very simply compile this one. So it just prints out hello. What do we expect from the Rust one? Okay, Rust hello. It didn't create any new threads. Well, that's good to see. Now let's move to the domains one. This will be the blocking call. Again, we have these three domains, and we use the request library, and we use it is by default an async, but there is a blocking version of it, and I just wanted to make a similar code as before, so we are using the blocking get, and then just prints out the status again. Let's build it. Okay, and now run again strace against it. Let's just run it. Okay, it works. And let's run strace against it. Domains. Are we making a new? Yes, we make a bunch of threads. If you remember, Python was the only one so far that did not create any new threads for these blocking calls. And we are especially calling request blocking. Oh my god. This is not what you would expect from a very popular Rust library, right? At least I don't. So I think we are creating around 6 threads. Let's do the same thing as with the Java. So let's run it and stop it. Okay, maybe I stopped it too fast. So I want to see some thread names. Hopefully we will see that. So where is my PS command? Okay, this was called domains. Yeah, we see enough. So it creates, for one request, it creates a request internal thread and a Tokyo runtime W. So my assumption is, and we could verify this in the strace output, but I will not open this, that for every get call, so we make 3 get calls, a new thread are created. One for the request internal and one for the Tokyo runtime. That's what we get. Let's move on to the coroutine version of this. Let's build it first, and then I will show the code. I actually will have 2 versions of this. because I just I wanted to make I was experimenting and wanted to see whether the thread count will be different if I use the libraries differently, and yeah, it was not. But I keep this code. So this was my first version, but it is like the blocking call except using async things. And this one uses futures and basically joins on all of them. So that's the slight difference in code. But in thread count, there is no difference. But you can play with this. I will share the code as usual below the video on GitHub. So this is the code. It uses async, so Tokyo runtime, and uses still the request library and awaits on those calls. We are not using the blocking version of it, so the default request library. Okay, let's see what happens. Too far. No, release. Let's run it. Okay, it still works. And let's trace it. Would you expect that? Oh my God, that's a lot. Okay, I calculate 34 new threads. That's huge. Oh, I'm sorry. I'm sorry. It's hard to justify this many threads. I can't justify this. And this is not Java. This is Rust. And by the way, this Rust has nothing to do with this. So this is about request and Tokyo, and probably mostly about request library. But still, that's not what I wanted to see here. Let's also run it and stop it, and hopefully we can see something. Okay, I stopped it. Where is my PS command again? Here it is. Yeah, now this is either Tokyo runtime or how request uses Tokyo runtime. I don't know where to put the blame. Okay, that's a lot. What else? Do we have other languages? So we looked at Python, then we looked at Go and Java and Rust. Yeah, I actually have a CPP version here. I will stop here. So in C and C++, the main problem is how the hell do you make a HTTP GET call in the first place? And there are some obvious candidates. You have to use a library, and there are some obvious candidates. Curl is one of them, one of the main solution for this. And I ran a version of that. And basically you get, there is no surprise there, nothing to learn, because it's just uses as many threads as you set up. It's very transparent. You can how you use it. So if it can use one threads for all of them, or it can use more depending on how you use it. Okay. So there were some surprises here. I created a table. Oh, sorry. So I created a table of the findings. So we have the hello world, the blocking version, and the coroutine version. And Python used 0, 0, and 3 threads. This was the async version, async IO. Go used around this many threads. Yeah, I did not talk about something that, so when I run strace against Go, then I see different versions, how many threads. And this was either because of strace, so maybe the thread, or because of the Go runtime. Based on, it can kick off new threads on its own if it detects a blocking call. And I don't know how that works exactly, and I just saw a hint of this in the blog, so don't take my word for it. I have to dig deeper into this, whether this was just an strace peculiar thing, or it was, or it's really changes by when you run it. that's all I want to say at this moment, because I did not dig deep enough. So then Java, yeah, specifically OpenJDK. Oh, and this was where I fell off the chair, but I did not show it to you because that was ridiculous. And what I did not expect it that Rust request and Tokio would be this bad. Bad in the sense that this sounds wasteful, and I can't really justify this. Yeah, and I also put various commands here, so I will put this in the code, and you can run it. Now the last thing I want to show is the actual threads. So man2 are for the system calls. As usual, these pages show both the libc calls, so the libc wrapper around the actual system calls and the system calls. So the documentation is nearly the same. There are some subtle differences between the wrapper and the system call. Sometimes the wrapper does some more things for you. So you can read the various things about the properties I mentioned earlier. So like the child does not inherit the parent's memory locks. Interesting thing. The pending signals is initially empty. So these are the various deeper things that I mentioned, that we could make a list of these various properties, and you could make an educated guess what makes sense to copy, what makes sense to not copy, and in the documentation you can go over these. Let's move on to the clone system calls. Yeah, there are at least 3 versions. And an interesting thing that the clone tree, you have to call it through a syscall wrapper, because it does not have it. It's not in the glibc yet. I don't know whether this is still true in the newer kernels, but in this Ubuntu version, this is still like that. And I want to show one particular things. Okay, one important thing about I think this is a nice takeaway, is that clone expects a stack for that thread. So there are you can send so this libc wrapper, it expects a function, so that's where the control will be taken. The thread will start in that function. That function will get a few arguments, and the clone system call itself has a few flags. I will show the flags a bit later, and you can set up the parent ID. This is for the thread local storage and the child thread ID. But the most interesting thing is that the stack, if you did not know about that, you actually have to allocate memory for this, and you have to point to the end of that memory, which is to the top, so the highest address of that memory, because the stack grows downwards, and there is no way here to send the size of the stack. So that's what clone tree, one of the things that clone tree fixed, is that if we go a bit deeper, so clone tree gets this big struct, and it gets the stack size. Earlier, the clone calls did not know about the stack size. Now, if you just think about it for a second, this is a big decision here when you create a thread. How big is the stack size? I mean, if it's usually you don't need a lot, so it can be a few kilobytes. But how the hell will you know? And do you have to make this decision? And of course, most languages hide this fact from you, but still, it's interesting to know about it. It's very different. It's a different thing than the main thread stack, which can even grow if you want. But growing a thread stack is really not possible in this with this system call. Okay, let's move on to the flags. Yes, so I want to show I will not go over them. Just want to show one very interesting one. So the clone files is about the file descriptors. So you get various ones immediately, like the standard input, output, standard error, and you can open a file, and then that will be a new file descriptor. File descriptors are just integers like 0, 1, 2, 3. And so what happens, how these file descriptors manage? So each process has their file descriptor table, and the file descriptor table actually points to another file descriptor table. I think it's called open file descriptors in the kernel. So those are actually pointers to the kernel. So let's think about processes. When you make a fork, you are copying the processes open file descriptor table, the processes file descriptor table to the new process. But these are pointers. They are still pointing in the kernel to the same thing. So some properties of file descriptors are stored here. Some properties of file descriptors are stored here. So what kind of things? Like, for example, in the kernel, the file offset, so where your cursor is in the file, is stored here. So a process gets a copy of the file descriptor table, and if both the parent and the child starts writing to a file, for example, they both see the changes in the file offset. So the cursor moves depending on either the parent or the child wrote, both sees that change. But if you change some flags, how you write, like making something like, okay, close on exec, so you add some flags to it, then those are actually recorded here. So if you make those changes in the parent and the child differently, they don't see that anymore. They don't see that change. Another thing they don't see is that if you create a new file or close a file. So let's take a look at closing a file. So here is the parent and the child. Originally they are the same. They are a copy of each other's file descriptors. And the parent closes a file. Well, it's just deleting a pointer to the kernel's open file descriptor table. It does not do anything. The child can still use that file. If the parent opens a new file, then it gets into its own file descriptor table, so there will be a pointer to the kernel's open file descriptors, and the child does not see that. So these are subtle differences. So what about threads? Threads actually share these file descriptor tables. So if you open or close a file or make any kinds of flags differently, or the file offset changes, everything is transparent to both the parent thread and the child thread. And this is where you can do you can create some Frankenstein's threads, like not setting clone files. So what would happen? So you set everything else for the thread as usual, like this, the VM and all the list I showed that are shared. And so your thread is not POSIX thread anymore, because you did not set this one. So it acts like a process in that sense. But as I showed previously, they look, unless you start creating new files, it acts very, very same than what you would expect, even though they have their own copy of file descriptors. But if the thread opens a new file and for example puts its file descriptor on the heap, so the parent can see that variable on the heap and sees that it's a file descriptor, but the parent actually can't read from it because it belongs to the child's file descriptor. So this file descriptor is not a valid file descriptor for the parent, even though it has access to it. And then the parent can also open a file, and it could have the same file descriptor because it's just an integer, and you get the next integer in that way. And then now you will have then suddenly it would the same memory would point to different files. So the parent and the child could reuse that memory, like this is file descriptor 3, and they are talking to different files. Obviously, this is not something you would want. But it's possible. You can create Frankensteins. Okay, I think it's time to close this. So what's the takeaway? So processes threads, there is a very simple mental model, which is the main difference, that threads are sharing memory, the processes don't. The processes get a copy of the memory, and this mental model is pretty good, but as I showed in the details, it is actually not correct, and you don't have to think about that at all. But it's good to know. It's good to know about them, because if you run into some corner cases when you really have to think about it, then you have to open the documentation. Another thing is that we saw these coroutines in various languages, and actually every coroutine version we saw. Let's take a look at again this document. Yes, they all used a lot more threads, or more threads than the blocking versions, which is quite surprising, because many times you see online that don't you use async because it's faster, because it doesn't use threads. I saw this argument, and if you look at the implementation, that's actually not true. And even if it were true, it's a really weird argument. So if you want to take advantage of the CPU, so for example, if you write a server, then you should use maybe even multiple processes, definitely multiple threads, just to be able to schedule all the things to all cores you have, and then maybe you can use coroutines internally. So you will use all three of these versions, but know about them. This is not use that one and not the other one. I mean, know that all of them has their own place. And coroutines have it's often syntactic sugar, which basically means that you get a big gun to your foot. So if that breaks down, then you really have to understand what's going on internally. If this syntactic sugar breaks down. That's all. Thanks for listening.